Convolutional neural networks, or CNN, are networks network architectures that is kind of basic. However, it is useful for many problems and can solve some problems of machine learning. Of course, now we have many complicated architectures and methodology in order to use deep learning for images. However, convolutional networks is a very useful method to give us results and to understand the basics of neural networks architecture for images. Now, a neural network like this will have, of course, the image as input, and of course, once we have the image, we have to extract some information out of it. The way we extract this information is by having different layers, because it is at the end deep neural network network, which is we start by extracting some information using convolution. And convolution we will explain every more in detail later. In short, it's simply a method to extract an image, some features from that input image. After the convolution, we try to reduce the size of our images, and with that we can do max pooling, and we keep doing convolution max pooling, depending on our design of a neural network. And after that, we have to take these kind of images that has some features, and what we will do is we will flatten these values, and once we have them flattened, we can pass them to a fully connected neural network, and then we can of course take decision based on what we discussed in the previous lecture. So the input image is the first part of this convolutional neural networks, and the input image can be simply the image in which we're trying to train or classify, and these values will be corresponded or represented by RGB, red, green, blue, or by different methods. We can also use HSV, in which of course RGB is simply the values of red, green, blue in the whole image, in the whole matrix, because it will become a matrix or a screen. Now HSV is simply H will be the color on which that cell will have, S will be how much is saturated, and V is how bright it is, or from black to complete white. So this is another way to actually get these or to represent the input of the images we have. Now, convolution, as we said, we try to extract some information. Now, to extract some information, we need multiple or many convolutions, that we will have the input of one image, but we will extract many convolutional images or channels, what we will call it channels, in which we will take this image and pass it through a kernel, and the kernel will generate another image. Of course, depending on the sizes, we can we have to go through all the images, and the way we do it, of course, if we have a kernel of a 3x3 kernel that is has this like weights, which is that we have one, for example, 1 0 1 0 1 0 1 0 1 this way, and we go through the first the corner of this screen, what we will find is we will have this value, this value, this value, and this value, and the middle value, and this will correspond to the value of 4. We keep doing this as we scan the whole screen, and we generate a convoluted feature that we want. As you can see, like in order to generate this feature, it will result in a smaller image. In order not to have such thing, what we sometimes do is we add padding, and as you can see here, this dotted lines are the padding, and the reason we added this is to preserve or to reduce the shrinkage of the image based on our kernel. So after the convolution, we do max pooling. Sorry, this is not cost function, it's max pooling. And the max pooling is basically we will take these channels and we will shrink the image size. So for example, if we have this convoluted result, we want to use max pooling. We call it max pooling, but of course it has many methods or different methods. For example, if we set our max pooling to be using actual max pooling, we simply take the highest value. And if we want to reduce or shrink this convoluted channels, we can also use average pooling, which is we take the average of all these values, and this will provide us another image, smaller, but will somehow have the features of the big image. The most popular is actually just using max pooling, getting the maximum value, and it will represent the bigger image features. Now, we keep doing this, as we said. After convolution max pooling, we do another convolution max pooling, and so on, depending on our design. And after that, what we will do is we will flatten these small images or filters. And the way we do it we will take the pooling layer, and then we will simply put this value will be 1, 0, 8, 5, and then the other value, let's say 2, 3, something in the other, in the one behind it, and we keep going this way. This flattened layer will be passed to fully connected neural network. So you will have these filtered or maxed pooling or pooled layers, and then we will have them flattened, and then we will pass them into the network, and at the end we will have our classes. So this way we can train our or this way we can build our network. Now there are some things we have to consider, because these things are more or less exist in most of or maybe even all the neural networks, which is first the dropout. And dropout is we try to reduce the overfitting of our solutions. So we don't want the matrix to be overfitted, just only good for the test, for the training data, and not good for the test data or other data that will come in the future. In order to do that, we randomly block some neurons as we in the training process, and we try to train the other part of the network to actually take the correct decision. So this is one of the practices we do. We call it dropout. Now, another thing is what we call patch normalization. And basically, as we already know, that normalization is trying to get the value from or getting the values of, for example, the input image between 0 and 1. In RGB, we have usually 200, or not usually, we have the image from 0 to 255 for the filters, the RGB filters. And then if we want to normalize it, we simply divide by 255. And this way, all the data in this screen, in this matrix, the image, will be from 0 to 1. Patch normalization will do the same thing. However, what it will do is we will do it inside this network. In the internal parts of the network, we will do patch normalization, and this is also improves our performance. Now, lastly, in the last layer, one of the very useful method is the softmax. And softmax is simply applying an equation in which we take every the final layer numbers, and what we pass them through the softmax based on the input vector of different of not just the actual neurons, but also the other neurons next to it. So if we're trying to classify the image of from 0 to 3. So for example, we have 0, 1, 2, 3. These are going to be calculated, the softmax value, which is actually, it's a little bit small here, but it's e to the power x, which is this value, divided by the summation of e to the power x of the whole matrix. So e to the power 3 plus e to the power 1.75 plus e to the power minus 2 and e to the power 0.5. We sum it, and this is how we get our output layer of max, soft max. Of course, this is for multi-class. If we're looking for only 0 to 1, which is like a binary, like either we have 1 or we have 0, we can use a sigmoid function.